Okay, now we have to determine if there's going to be a precipitate for this reaction. I'm going to write up here so it's lead chloride that we're going to be making by putting lead ion and chloride ion into solution together. We're going to mix them together. They start out apart. Sodium, the chloride is in the sodium, which is soluble, and the lead is in the lead nitrate solution, so that's soluble, and then we mix them together. So we're mixing, so we're going to have to convert to moles, as we've done before, to find the new concentrations, and then those concentrations are going to go into our QC expression, and if QC is greater than KC, or KSP I should say, then there's going to be a shift left, and this is a solid. It's going to be a shift left, and so if QC is greater than KSP, we go back to reactants, which are solids, so we're going to get a precipitate, PPT. Now, I used to just call it lowercase PPT, and that's in older books. I just looked to check on that because PPT is also a PowerPoint, and they recommend making it a capital P. I probably won't follow that up, but that's what we're after. So if QC is less than KSP, then no precipitate. So that's what we're going to be doing here. So since we have to mix them together, we have two different solutions, one that contains sodium chloride, one that contains lead nitrate. Mix them together, check out the concentrations of the lead and the chloride, put them into our QC expression, and compare it to KSP. And we'll find out what that KSP is 1.60 times 10 to the minus 5. Let me double check that. Well, it sounds fine. Okay, so we have this. And that's going to give us 1.50 times 10 to the minus 4 moles of chloride ion. And then, yeah, I focused in a little bit closer to the paper. So I'm going to keep checking from time to time when I kind of pause. That's me just making sure everything's on the page. Now, those are our concentrations once they've been mixed on their own, I should say. They're in each of their beakers. That's how many moles are. And then when we mix them together, their new concentrations are going to be those moles divided by our new volume. And our new volume is 40 times plus 50 mils, or 90 mils, or 0.09 liters. And then this is 2.00 times 10 to the minus 5 moles of lead. I'll try to remember to put in the species each time, but if not, you should be able to follow it. Move this over slightly. And this comes up to be 1.67 times 10 to the minus 3 molar Cl minus. And this is 2.22 times 10 to the minus 4 molar lead. Okay, and then our QC expression, taking it from up here, would be the concentration of the lead ion times the concentration of the Cl. So when we mix those together, what we see as a precipitation is, or a possible precipitation, is just not being at equilibrium anymore. So when we mix them together, we have a certain concentration of lead and chloride. Maybe it'll stay in solution because there's not enough ions to force it back to the left, or maybe it will precipitate out. So a precipitation reaction is just one that wasn't at equilibrium, and that's what we're going to determine here. So this is the reason why we have a precipitation, is that the QC is greater than KSP. We shift back, according to Le Chatelier's principle, back to the reactants, and the reactants happen to be solids, a solid here, and so we get we see solid form. Just to make sure I got everything in the right spot. And then this is equal to 6.19 times 10 to the minus 10, and QC then is less than KSP. So no precipitate. I'm just going to use lowercase ppt. Used to that. Okay, so let's try another one. My guess is that this one is going to precipitate because you know, if I'm going to do 2 of them. But there's no guarantee of either way on the exam. So I made a mistake on, I started writing on the printout that I made. I'm just going to leave it like this. We have a beaker that contains 35 mils of 0.004 magnesium nitrate, 25 mils of 0.0003 molar sodium arsenate. We mix those together. Do they precipitate out? Let's find out. So it's shorthand here, but definitely should be able to follow it. It's the same exact data, types of data that you had in the last one. Now, the big thing is determining what the ion is. Well, the sodium and the nitrate, as we know from the solubility rules from chapter 4, they aren't going to react with anything. So really, as soon as you see sodium and nitrate, you can take them out of the equation or out of the system. It's magnesium and arsenate. Then look in your table and you see, oh, magnesium arsenate. That tells you that this is the expression. And QC is going to be the concentration of arsenate squared times the concentration. Since we're mixing them, there's no guarantee we're at equilibrium. We might be just by chance, but there's no guarantee. So the concentration of magnesium is the same as the concentration of the magnesium nitrate. It's 1:1. Now, if there had been a 2 here, then we'd have to double the concentration. So keep that in mind. But here there's just 1 arsenate, 2 per formula unit, so it has the same number. But if this had been a 3 here, then we multiply this number by 3, so just be careful. I can't do every possible combination. I wish I had done one like that, but you know, I just mentioned it here. You should be fine. Now, but these concentrations don't go directly in here because we have to mix them. So we have to change to moles. So first, and then divide by the new volume to get the new concentration. So we have the magnesium and times its volume. So anytime there's mixing involved, we have to change to moles. There may be an exception to that, but I can't think of any offhand, and every time we come across it in titrations or here, or just mixing 2 solutions together, it's always come out where we had to convert to moles. And so at least for us, we're always going to have to convert to moles when we mix. And then this comes up to be 0.02. And this is 7.5 times 10 to the minus 6 moles of arsenate ion. Make sure that we're on the page. Yep. And then 1.40 times 10 to the minus 4 moles of magnesium ion divided by the new volume, which is 60 mils, or 0.06 liters. And this gives us 0.00233 molar magnesium ion. And then we have 7.5 times 10 to the minus 6 moles of arsenate ion divided by 0.0600 liters. And we come up with 1.25 times 10 to the minus 4 molar arsenate. And if I'm not on the page, I make sure that I am. There we go. Now those are our concentrations once they've mixed, so we can put them directly into the QC expression above here. Put those numbers in. The arsenate goes in first, and it's raised to the 2nd power. And the magnesium goes in second, raised to the 3rd power. And I get 1.98 times 10 to the minus 16, and that means QC, I didn't put it up here, but where's KC? Or did I put it up here? No, I didn't. Okay, so KSP, I should say, for magnesium arsenate is 2.00 times 10 to the minus 20. That's what we're comparing. QC is greater than KSP, and make sure you recognize that. You see that 20 there, that throws people off, but remember it's negative 20. The larger a negative number is, as an exponent, the smaller it is overall. It's so this is much larger actually by 4 orders of magnitude. So there is definitely precipitate. And I'd accept that as that's fine if you want to put in just PPT, or yes, there is PPT. And that is the deal. Let's see.